All right, in this video, we are going over section 4.3, which is on maxima and minima. And we are going to try to complete these learning objectives. So we will define what absolute extreme values are, absolute extrema. We will define local extrema. Local and absolute are a little bit different. And then we'll explain how to find critical points of a function over a closed interval. And then finally, we will explain or describe how to use those critical points to find absolute extrema over a closed and bounded interval. Okay, so in this video, we're not going to read the whole text, but we'll go over the important definitions and theorems and then some practice problems. Okay, so let's start here with a definition. We have a function f that is defined over an interval I. And then there's a special value in that interval called c. So we say that the function f has an absolute maximum on that interval I at c if the function value, the y value for c, is greater than or equal to every other function value f of x for all x values in the interval I. Okay, so just to draw, a picture of what we're saying there, let's suppose that we have a function that does something like this. And then let's suppose that the function ends at these endpoints here. So the interval I could be starting from, let's say, from this value A to this value B. And so we would say that there is an absolute maximum here at an x value of c because this value here, f of c, the y value corresponding to c, is larger than any other y value. You can pick other y values, no matter which y value you pick, which point you pick on this graph, the y value will be less than or equal to f of c. And we can see a couple of them. Here are the y values. We can see that they're lower than f of c. Okay, so similarly, we define an absolute minimum on I at C if that y value is less than or equal to any other y value for any x value for all x values in the interval I. The absolute maximums and absolute minimums we call absolute extrema. Extrema is plural, extremum is singular. Okay, so um, yeah, let's take a look here. Just very quickly, it says the term absolute here does not refer to absolute value. An absolute extremum may be positive, negative, or zero. Yeah, it's very possible that the even the absolute maximum, it's possible, is a negative value. If you take a look at the graph, here in blue, the absolute maximum for this function here is going to be some negative value. So that's very possible. Okay, so let's move on. This is very good reading material if you want to read through this yourself. Um, so let's go ahead and take a look at the extreme value theorem next. This is theorem 4.1, the extreme value theorem. So how do we find extreme values or absolute extrema on for a function f? Well, let's take a look at this theorem. And what it says is, if you have a function f that is continuous, so it's important that the function is continuous, And if it is defined over a closed and bounded interval from A to B, then there must be a point in the interval from A to B where f has an absolute maximum and where f has an absolute minimum. Okay, so if we satisfy the conditions where that f is continuous and it is defined over a closed and bounded interval from A to B, then it is guaranteed to have an absolute maximum and an absolute minimum. Okay, so let's go ahead and take a look at a couple of examples just very quickly here in the textbook. And so let's start with, um, we can start with f of x equals x minus 2 squared. We know that that's a parabola. And if it's constrained to the interval from 1 to 4, notice that that is a closed interval, since we have these square brackets, and it is bounded. It is not infinite. It is bounded by the numbers 1 and 4. And so the extreme value theorem guarantees that there must be an absolute maximum and absolute minimum. And if you take a look at the graph, the absolute minimum occurs um, there. The absolute minimum value is 0, occurring at x equals 2. And there's an absolute maximum of 4, yeah, occurring at x equals 4. Okay, so the absolute extreme value is the y value, and the location at which occurs, can be stated as well. That's an x value. Okay, so um, now these other graphs are good to look at as well. So we can look at D very quickly. This function here, if you take a close look at it, um, this is a piecewise function, and you could figure out that this function is not continuous over the interval from 0 to 4. Okay, we can see that the limit as x approaches 2 from the left-hand side of this function is -2, and the limit as x approaches 2 from the right side of this function is equal to -1. Since these limits are different, then we have a jump discontinuity. That's something we've talked about before. Because we have a discontinuous function over the interval from 0 to 4, the extreme value theorem is not going to guarantee absolute maximum and an absolute minimum. Okay. Now, if we take a look at this graph, we can see that there actually is an absolute maximum. So they may still occur, but the absolute max and min are not guaranteed by the theorem. It still has an absolute max, but an absolute minimum it does not have because it looks like the minimum value, it wants to be -2, but the function will just continue to approach -2 forever, getting closer and closer without actually ever reaching it. Okay, so the limit here as x approaches 2 from the left is -2, but the value -2 isn't actually ever taken on by this function on this interval. Okay, so notice there is no absolute minimum. Yeah, and it's not guaranteed at all by the extreme value theorem since one of the conditions of continuity is not met. Okay, and as we said, there can still be, it's possible that there still would have been an absolute maximum and as absolute minimum, but after further inspection, there was an absolute maximum, not an absolute minimum. Okay, and then finally the third function here, um, we have x over 2 minus x on the interval from 0 to 2. Now, the extreme value theorem does not apply to this function on this interval because um, the function is continuous on the interval, but the interval is not closed. We have this 2 with a round parentheses on it. And so the extreme value theorem does not apply. Therefore, we are not guaranteed to have an absolute max and absolute min. So absolute max and absolute min are not guaranteed. Okay, so they might still occur. And as we can see from the picture, there is an absolute minimum of 0 at x equals 0. And uh, is there an absolute maximum? No. It looks like there's an infinite discontinuity. The function continues to increase without bound as x approaches 2 from the left. Okay, so there was an absolute minimum, no absolute maximum. So yeah, that's a pretty cool theorem. Whenever you're dealing with a continuous function on a closed and bounded interval, the absolute extrema, maximum and minimum, are guaranteed. All right. We won't read all of this. Uh, okay. So then we have another definition here, and that is of a local extremum. And so similarly, we can define the local maximum at C if there exists an open interval I, if we can make a little open interval I containing C such that I is contained in a domain of F and f of C is larger than or equal to f of x for all x values in the interval I. So what that means is just, let's take this value here and we'll call it C. It looks to be 0, but we'll just say C. If we can make an interval, let's say, from A to B, and this interval is being called I here in the definition, but if we can make an interval, and it does say open interval, so let me change that notation from A to B, uh, such that this y value, f of c, is larger than or equal to any other function value, I'll call this one here f of x, for any x value in the interval from A to B. Notice that f of c is larger. Now, so we would say that this is a local maximum because locally, f of c is larger than everything else nearby. But it is not the largest of the points on this function. It is just the largest y value over some open interval uh, around c. Okay, so um, we would say f of c is the largest y value in its neighborhood, right, nearby. Okay, so a local minimum is defined in a very similar way. Local minimum at C, if we can make an open interval I that contains C such that I is contained in the domain of F and f of C is less than or equal to f of x for all x in the interval I. A function f has a local extremum at C if f has a local maximum or local minimum at C. All right, nice. So in this case, this, oops, wrong tool. In this case, here, uh, f of 2, this point, 2f of 2, would also be a local maximum. All right. And then just a quick note here. It says if f has an absolute extremum at c and f is defined over an interval containing c, then f of c is also considered a local extrema. And here's a good note. If an absolute extremum for a function f occurs at an endpoint, we do not consider that to be a local extremum, but instead refer to that as an endpoint extremum. All right, very good. So, um, how do we find these local extrema or even absolute extrema? Well, we need another definition to get to that point. And so, uh, our definition is actually going to be motivated by this picture here. We can see that there's a local maximum at 2f of 2 and another local maximum at that f of c, which is like 0f of 0. And what we'll notice after doing a few problems where we find local minimums or local maximums is that a local minimum or maximum will occur whenever the slope of the tangent line is equal to 0. Oh, and yeah, maybe I misworded that a little bit. A local minimum or local maximum can only occur when the slope of the tangent line is equal to 0 or if the slope of the tangent line is undefined. Now, they won't, the slope of the tangent line being equal to 0 is not enough to tell us that a local extreme value will exist, but it is a necessary condition. So, uh, yeah, here we can see at this local max, the slope of the tangent line is equal to 0, or if we want, f prime of c is equal to 0. And then the uh, f prime of 2 is undefined. Okay, we can see since there's like a bit of a corner or a cusp there, um, the derivative is undefined. And that also is kind of a clue that there might be a local max or local min there. Okay, so we are going to give another definition. Let C be an interior point in the domain of F. So it's not one of the endpoints. We say that C is a critical point of F if the derivative at C is equal to 0 or the derivative at C is undefined. Okay, I'll highlight, triple highlight the undefined. That's the one that gets forgotten the most often. But um, if the derivative is 0 or if the derivative is undefined. As mentioned earlier, if f of c has a local extremum at a point x equals c, then c must be a critical point of f. This fact is known as Fermat's theorem. Okay, so what is Fermat's theorem? Uh, if f has a local extremum at c and f is differentiable at c, then the derivative at c is equal to 0. Okay, nice. Yeah. And if it has a local extremum uh, at C, we could also say it's also possible that f is not differentiable at C. If f is differentiable at C also, then the derivative must be 0. And there's a nice proof for that here in the book. We can skip that. So here are a couple of uh, examples. These are very nice because uh, if the derivative is equal to 0, we might have a local maximum as occurs in this first picture. Or if the derivative is undefined, we might have local maximum or local minimum at that point. Here's another one where the derivative is undefined. Looks like an absolute value kind of function. And there is a local minimum at that critical value. But we did say just because the derivative is equal to zero, as it is in this picture here, that does not necessarily mean that there's going to be a local max or local min there. It is possible, as in part D here, that there's no local extreme value at C, even if the derivative is equal to zero. And here's another example of where the derivative is undefined. There is a vertical tangent line, so the slope is undefined, the derivative is undefined. But you can see from the picture that's neither a local max nor a local min at this point here. So we would say there's no local extremum at C. All right. So uh, let's take a look at some of these examples. So there's some nice examples here. Let's go ahead and take a look at a couple of these. We'll do maybe let's do B and C. Okay, so let's see what it says here. For each of the following functions, find all critical points. Use a graphing utility to determine whether the function has a local extremum at each of the critical points. Okay, so if f of x is equal to x squared minus 1 quantity cubed, then f prime of x, we'll have to use the chain rule here. This is 3 times x squared minus 1 raised to the second times the derivative of the inner function, which is 2x. Okay, we can set this derivative equal to 0. This derivative is never undefined because it's a polynomial. It's defined everywhere. Um, and so what we get is x squared minus 1 squared equals 0, or 2x equals 0. And if you want to set the 3 equal to 0 also, you can do that. 3 equals 0, that's just false, so we won't get any solutions from that. X squared minus 1 squared, we can take the square root of both sides. And I'm also going to factor the x squared minus 1. That is a difference of squares, so we get x minus 1 times x plus 1 equals 0. Or if we divide by 2 here, we get x equals 0. So we have x equals positive 1, or x equals negative 1, or x equals 0. These three are our critical points. So there may or may not be extreme uh, local maxes or mins uh, at these three x values. Um, and there's a way to determine this. I will leave it to I'll wait till section 4.5, and we can just look at the graph. We found the critical points. That's what we were asked to find. And then use a graphing utility to determine whether the function has local extremum at each of the critical points. In section 4.5, we will go over a method for doing this without a graphing utility. But for right now, we'll leave it at this. So let's go ahead and scroll and see if any of these three are local max or min. Okay, so for part B, we can see it says this function has three critical points. Okay, we found them, x equals 0 and plus or minus 1. The function has a local and absolute minimum at x equals 0. So we can see that, but does not have local extrema at the other two critical points. Okay, so interesting. Uh, only one out of the three was a local max or minimum, and the other two were just they were critical values, critical points, but didn't end up producing any local extrema. Okay, cool. How about part C? Well, that's a good exercise here, so let's take a look. The derivative, f prime of x, is going to be, we're going to use the quotient rule. So f prime times g minus g prime times f, all divided by g squared. There's our derivative function. We can go ahead and clean that up a little bit. Um, what do we get here? 4. Let me write it above here, just so I don't have to write it a bunch of times. This is going to be 4 plus 4x squared minus 8x squared. And so what we end up getting there is, after simplification, is a minus 4x squared plus 4 divided by 1 plus x squared squared. Excuse me. Now, if we factor out a negative 4 from the numerator, we get x squared minus 1 over 1 plus x squared squared. And we can factor, that's already a difference of squares that's come up in the previous part. This is x minus 1 on top times x plus 1 divided by, and now 1 plus x squared squared, that's never going to be equal to 0, right? So I was hoping that this quotient function here uh, would end up being undefined for some x values, but the denominator, no matter what number you plug in here for x, whenever you square it um, and then add 1, you're always going to get a positive number. So, the denominator is never equal to 0, so this function is never undefined, but we can set this equal to 0 and find some critical values where the derivative is equal to 0. They are going to occur when x minus 1 equals 0 or when x plus 1 equals 0. So x equals plus or minus 1. And they were called critical. When I took this class, they were called critical values, but critical points, you can call them that too. Yes. Okay, so at plus or minus 1, do we have local max or mins? Well, let's take a look. Let's take a look at the graph here. It looks like we have a local minimum at one of them and a local maximum at the other. In section 4.5, we're going to take a deeper dive into looking at the derivative, and we'll look at the derivative being negative and then positive, implying that there is a local minimum. And then the derivative being positive and switching to negative will imply the existence of a local maximum. But we'll talk about that. That's called the first derivative test in section 4.5. Okay, so finally, locating absolute extrema. So, how do we find these absolute extrema that we defined at the beginning of this video? Well, there's a theorem that allows us to find the absolute extrema for a particular type of function defined over a particular type of interval. And so theorem 4.3, location of absolute extrema. If f is a continuous function, triple highlight that, continuous function, over a closed and bounded interval I, so again it has to be closed and bounded, then the absolute maximum of f over I and the absolute minimum of f over I must occur at the endpoints of I or at critical points of f in I. Okay, so yeah, so then we're given a problem-solving strategy here. Uh, this theorem guarantees us that the absolute extrema will be located at the endpoints or at the critical points. And so, well, then what we can do to solve these kinds of problems is just evaluate the function f at the endpoints of the interval from A to B, so x equals A and x equals B. Then we can find the critical points of f and evaluate the function f at those critical points. And one of those points from parts one and two, from steps one and two, will have to be the absolute maximum, and one of those will have to be the absolute minimum. So step three says compare all values found in steps one and two. The absolute extrema must occur at the endpoints or critical points. Therefore, the largest of these values is the absolute maximum of f, and the smallest of these values is the absolute minimum. Okay, so let's go ahead and take a look at a more complicated problem here. We can take a look at part B because it's a little bit more complex than part A. And just to finish this up. So part B says for each of the following functions, find the absolute maximum and absolute minimum over the specified interval and state where those values occur. Okay, so here's a function. We're given the function f of x equals x squared minus 3x to the 2 over 3 over the interval of 0 to 2. Okay, so we can find the, so let's go ahead and do it based on this problem-solving strategy. We're told that the absolute maximum might occur at the endpoint. So what we should do is we should evaluate f at 0. That's going to just be 0. Uh, what's the other endpoint? 2. So f of 2 is 2 squared minus 3 times 2 to the 2/3. And so this is going to be equal to 4 minus 3 times the cube root of 4, 2 squared, right? And we'll figure out what that is here. Let's see, I have my calculator with me. Let me punch that into a calculator. 4 minus 3 uh, times 4 raised to the 1/3 times 4 raised to the 1/3. So I'm getting here approximately negative 0.7622. And let's just make sure that that's, let's see if that comes out here. 0.76. Yes. Okay, nice. So those are that, we've evaluated f at the endpoints. Now, we know that the extreme, uh, the absolute maximum and absolute minimum could occur at critical points. So we should also find the critical points. That requires us to find the derivative. The derivative is 2x minus 2x to the negative 1/3. And here we finally have, x to the negative 1/3. That is going to be, let's see here, 2x minus 2 over x to the 1/3. We need to get a common denominator, so I'm going to write 2x over 1 and multiply that by x to the 1/3. The x on top right now is x to the 1, and so that gives us, let's see here, I'll do this on the side. X to the 1 is the same as x to the 3/3 times x to the 1/3, and so that's going to be x to the 4/3. So we end up getting 2x to the 4/3 minus 2 divided by x to the 1/3. They have a common denominator, so we can combine the numerators, and this is 2x to the 4/3. Oops, let me factor out a 2. X to the 4/3 minus 1 over x to the 1/3. Okay, so now we can find the critical points. Remember that the critical points are where this function is equal to 0, and that would be where the numerator is equal to 0. So f prime of x equals 0 is the same as just setting the numerator equal to 0. So let's figure out what that would be. If we divide by 2 on both sides, we get x to the 4 thirds minus 1 equals 0. Add 1 to both sides, x to the 4 thirds equals 1. And then finally, we can see, hopefully we can see here um, that the solutions are x equals plus or minus 1. If we raise positive 1 to the 4 thirds, that's equal to 1. And if we raise negative 1 to the fourth power, that's positive 1. And then raise to the 1/3 is still positive 1. So, yeah, the solutions here are x equals plus or minus 1. Now, the interval that we're considering is from 0 to 2. So we really shouldn't even need to consider the negative 1 here, but it did end up coming up as a critical point. We can kind of ignore it if we want. Okay, so finally, f prime of x is undefined if its denominator is equal to 0. And so if x to the 1/3 equals 0, we can see that uh, that is going to imply that there is a critical point. And if we solve this equation here, cube both sides to get x equals 0. So the critical points are positive 1, 0, and negative 1 is a critical point, but it's not in our interval, so we'll just ignore it. All right, and then 0 we've actually already checked because that was one of the endpoints. So we already checked the function's value at 0. And so the last step here, once we find the critical points in step 2, now we evaluate f at those critical points. So let's go ahead and evaluate f at positive 1. F of 1 is 1 squared. And you know what? Let me write it up top in green. F of 1 is equal to 1 squared minus 3 times 1 to the 2/3. This is going to be just 1 minus 3, and so that is negative 2. So among these three values here, one of them has to be the absolute maximum, and one of them has to be the absolute minimum. All right, so the absolute minimum is just the lowest of these values. So absolute min is negative 2 at x equals 1. And the absolute maximum, the largest value here, is 0 of 0 at x equals 0. All right, let's double check our answer over here. Hopefully they have a graph. There's our graph. The absolute maximum occurs there. Nice. Absolute minimum is negative 2 at x equals 1. And this other point is just an endpoint. I mean, okay, nice. It's not part of the answer, but um, we know what the coordinates of the point are because we evaluated the function f at the endpoints. All right, cool. All right, let's just read this last paragraph here to finish the video. It says, at this point, we know how to locate absolute extrema for continuous functions over closed and bounded intervals. We have also defined local extrema and determined that if a function f has a local extremum at a point C, then C must be a critical point of f. However, C being a critical point is not a sufficient condition for f to have a local extremum at C. Later in this chapter, section 4.5, we show how to determine whether a function actually has a local extremum at a critical point. First, however, we need to introduce the mean value theorem, which will help as we analyze the behavior of the graph of a function. Okay, nice. All right, so that'll be the end of this video. Hopefully you enjoyed it. If you did, leave a comment or something on the video or a like, and I will continue to produce these videos. All right, see you in the next one.